What if everything you knew, every moment, every memory, every breath, could vanish in an instant? The end of time isn't just a plot from science fiction or the stuff of ancient prophecies. It's a question that's haunted humanity for centuries, whispered in the ruins of lost civilizations, and scribbled in the margins of modern scientific papers. From the Mayan calendar's ominous predictions to Einstein's equations hinting at the collapse of spacetime itself, we've always been obsessed with one terrifying possibility: that time itself could stop. And here's the chilling part: it might not be as far-fetched as you think. Scientists, philosophers, and even theologians have wrestled with this idea, painting scenarios so bizarre they defy imagination. Picture this: a cosmic freeze where every atom grinds to a halt, or a violent collapse where the fabric of reality unravels in seconds. Some theories suggest time could loop endlessly, trapping us in an infinite rerun of existence, while others warn of a silent, creeping void where the universe simply forgets to continue. And that's just the beginning. Today, we're diving into 30 of the most mind-bending theories about how time might meet its end, each one stranger and more unsettling than the last. This isn't just about doomsday predictions or abstract physics. It's about the very nature of reality, what it means to exist, to remember, to be. Because if time can end, what does that say about everything we hold onto? The answers might terrify you, but they'll also leave you in awe of just how fragile and extraordinary our universe truly is. So buckle up. By the end of this journey, you'll never look at a clock or the stars the same way again. The first stop on our journey into the end of time takes us to one of the most dramatic possibilities: the Big Crunch. Imagine the universe running in reverse, like hitting rewind on the greatest cosmic film ever made. Instead of expanding endlessly, galaxies stop fleeing from each other and begin to creep back together. Stars, planets, even the fabric of space itself gets pulled inward by an unstoppable gravitational embrace. Over billions of years, everything we know, every constellation, every black hole, every speck of stardust collapses into a single, infinitely dense point. The universe would essentially undo itself, vanishing back into the singularity that birthed it. This isn't just poetic speculation. For decades, scientists seriously debated whether gravity might eventually overpower the universe's expansion. Think of it like tossing a ball into the air. What goes up must come down, right? If there's enough matter in the cosmos, gravity could reverse the Big Bang's explosive momentum, dragging everything home in a cosmic collapse. Early cosmologists called this the closed universe model, where space curves back on itself like the surface of a sphere. But here's where things get murky. Modern observations of distant supernova suggest the universe isn't just expanding, it's accelerating, as if some invisible force is pushing it apart faster and faster. That force, we call it dark energy, and its existence throws a wrench into the Big Crunch theory. If dark energy keeps winning this cosmic tug of war, gravity may never get the upper hand. But some physicists aren't ready to rule out the crunch just yet. What if dark energy weakens over time? What if unknown quantum effects kick in at scales we can't yet measure? The debate rages on, with equations scribbled on blackboards across the world trying to answer one haunting question: does the universe have an expiration date? And then there's entropy, the slow, inevitable march toward disorder. Even if gravity could reverse the expansion, entropy poses another hurdle. The universe loves chaos, and reversing that would be like unscrambling an egg. Some theories suggest a crunch might not reset time, but instead lead to a chaotic, boiling mess of energy, a big splatter, rather than a clean rebound. Others speculate that the collapse could trigger a new Big Bang, birthing another universe in an endless cycle. Imagine that, our ending becoming someone else's beginning. The Big Crunch isn't just a scientific hypothesis, it taps into something deeply human. The idea of everything we've ever known collapsing into darkness is terrifying, but also strangely beautiful. It's a reminder that existence might be cyclical, that endings can birth new beginnings. And if that's true, then maybe time isn't ending at all, or just transforming. If the Big Crunch offers a dramatic, fiery finale for the universe, then heat death is its polar opposite, a slow, silent fade into nothingness. Picture a cup of coffee left on the counter. At first, it's steaming, full of warmth and energy, but leave it long enough and it cools to room temperature, blending into its surroundings until you can't tell where the coffee ends and the air begins. Now imagine that happening to the entire cosmos. This is the grim fate known as heat death, where entropy, nature's relentless drive toward disorder, wins the ultimate battle. Here's how it works. Every star, every galaxy, every flicker of light is essentially a pocket of concentrated energy. Over trillions upon trillions of years, these pockets will gradually deplete. Stars will burn out, black holes will evaporate, and even the fundamental particles holding matter together may decay. The universe won't explode or collapse, it'll simply exhaust itself, like a wind-up toy winding down for the last time. Space will become a vast, featureless void where temperatures hover just above absolute zero. No heat, no light, no movement, just eternal stillness. This idea isn't some dystopian fantasy. It's rooted in one of physics' most unshakable laws, the second law of thermodynamics. It states that in any closed system, entropy always increases. Think of entropy as cosmic wear and tear. Every time energy is used, some of it becomes unusable, dissipating into the environment as waste heat. Eventually, there's no usable energy left. The universe, in essence, becomes a graveyard of equally distributed, useless warmth. But what would this actually look like? Imagine drifting through space billions of years from now. The sky, once glittering with stars, would be pitch black. The last remnants of civilization, if any still exist, would huddle around the fading embers of black holes, the only remaining sources of energy. Even those would eventually vanish thanks to a phenomenon called Hawking radiation. When the final black hole winks out of existence, the clock might as well stop. Without energy gradients, without hot and cold, high and low, nothing can happen. Time itself could lose all meaning because change is no longer possible. Some theorists argue this fate is unavoidable given what we know about physics. Others propose loopholes. Could quantum fluctuations spawn new universes in the void? Could intelligent civilizations find a way to cheat entropy, perhaps by harvesting energy from alternate dimensions? These questions linger at the edge of science fiction, but they underscore a profound truth. Heat death isn't just about the end of stuff, it's about the end of possibility. No more births, no more deaths, no more stories, just an endless uniform silence. Yet there's a strange poetry to this theory. In a way, heat death is the universe's most democratic ending. No explosions, no violence, just a quiet reconciliation where everything, from the mightiest galaxy to the smallest atom, reaches the same equilibrium. It's a reminder that even in the grandest scales, the universe obeys simple, inexorable rules. And while the timeline is unimaginably long, so long that human history would barely register as a blip, it forces us to confront a humbling thought. All our struggles, our triumphs, our art and science and love might one day leave no trace at all. But here's the twist: heat death might not be the final word. Some models suggest that in a universe devoid of change, quantum randomness could eventually spark a new Big Bang. It's like waiting for a deck of cards to shuffle itself back into order by pure chance. The odds are astronomically low, but given infinite time, even the impossible becomes inevitable. So perhaps in the deepest cold, the seeds of a new beginning lie dormant. The end of time might just be a prelude to time's rebirth. While heat death paints a picture of the universe fading quietly into the void, there's another fate that's far more violent: the Big Rip. Imagine dark energy, that mysterious force pushing the cosmos apart, growing stronger over time. not just gently accelerating the expansion, but turning into an unstoppable cosmic hurricane. Galaxies would first drift apart, then stars within them would be torn from their orbits, planets would be shredded from their solar systems, and in the final moments, even atoms, the very building blocks of matter, would be ripped apart as the fabric of space-time itself fractures. This isn't destruction, it's annihilation on a scale so absolute it defies comprehension. The Big Rip hinges on a specific property of dark energy called its equation of state. If this value dips below a critical threshold, dark energy's repulsive force wouldn't just outpace gravity, it would intensify exponentially. Think of it like stretching a rubber band. At first, it resists, but pull hard enough and it snaps. In this scenario, the universe isn't just expanding, it's being pulled apart from the inside out. Mathematical models show that if dark energy behaves this way, the end wouldn't be billions of years in the future. It could happen in a cosmically brief instant, perhaps just tens of billions of years from now. For context, our universe is currently around 13.8 billion years old. That means the Big Rip could be closer than we think. Observational evidence adds chilling weight to this theory. Measurements of distant supernova and galaxy clusters reveal that the universe's expansion is accelerating, and dark energy's influence appears to be growing. The question isn't just if dark energy will dominate, but how it will dominate. Will it plateau, leading to heat death, or will it spiral out of control, triggering a rip? Right now, the data is tantalizingly ambiguous. Some studies of cosmic microwave background radiation hint at dark energy's equation of state being close to the critical threshold, close enough to keep physicists awake at night. But here's the most unsettling part. In a Big Rip scenario, time wouldn't just end, it would lose all meaning before the finale. As space-time stretches toward infinity, light from distant objects would redshift into oblivion. Communication between particles would break down. Even causality, the fundamental link between cause and effect, would dissolve. The universe would become a collection of isolated fragments, each unaware of the other's existence, until finally, everything is reduced to a soup of unbound quarks and radiation. Could we survive it? Not a chance. Long before atoms disintegrate, the cosmic forces holding our planet together would fail. Then our molecules, then our nuclei. The rip wouldn't just end life, it would erase the conditions necessary for life to ever exist again. It's a hard reset on reality itself, yet amid the horror, the Big Rip offers a strange kind of closure. Unlike heat death, slow decay, the rip is decisive, a clear, if brutal, finale. And in a way, it mirrors humanity's own existential dread, the fear of being torn apart piece by piece until nothing recognizable remains. But there's another twist. Some models suggest that if dark energy's behavior changes again after the rip, the torn fragments of spacetime could seed new universes, each born from the wreckage of the old. Destruction and creation locked in an endless dance, the Big Rip might not be the end. It might just be the universe's way of starting over. One thing's certain, whether the universe ends with a crunch, a whisper, or a scream, the very fact that we're here to ponder it is nothing short of miraculous. Now let's turn to a theory that makes the Big Rip look almost gentle: vacuum decay. Picture the universe like a frozen lake on a barely sub-zero morning. The ice seems solid, stable, but under the surface, unseen forces could be at work. A single crack, a single shift in conditions, might trigger a catastrophic chain reaction, spreading unstoppably until the entire lake shatters. That's vacuum decay, a quantum apocalypse where the very laws of physics rewrite themselves in an instant, wiping out existence as we know it. This nightmare scenario hinges on something called the Higgs field, an invisible energy field that permeates all of space. It's the reason particles have mass, the glue holding reality together. But here's the terrifying part: the Higgs field might not be in its true lowest energy state. Think of it like a marble resting in a shallow dip on a hillside. It's stable for now, but a nudge could send it tumbling into a deeper valley, a true vacuum. If that happens, a bubble of this new, lower energy state could form somewhere in the universe, and once it does, physics as we know it would unravel from the inside out. The bubble would expand at the speed of light, rewriting the fundamental constants of nature in its wake. Atoms gone, the forces that bind them redefined. Even time and space would cease to function as they once did. You wouldn't see it coming. One moment, everything's normal. The next, an invisible wall of annihilation sweeps through, leaving nothing recognizable behind. What makes this especially chilling is how random it could be. Unlike the slow march of heat death or the visible signs of a big rip, vacuum decay could begin anywhere, anytime, triggered by a single quantum fluctuation in some distant galaxy. And because it moves at light speed, we'd have zero warning. The first sign of disaster would be the disaster itself. Scientists aren't just spinning horror stories here. Particle colliders like the Large Hadron Collider have spent years testing the stability of the Higgs field. So far, the data suggests we're probably safe. The Higgs seems to be in a metastable state, meaning it's stable enough for now. But for now is doing a lot of work. The universe is old, but it's also vast. Over deep time, the odds of a quantum-triggered catastrophe creep upward. Could we stop it? Almost certainly not. The energy released as the bubble expands would dwarf anything in nature, rewriting reality itself. Some have speculated that advanced civilizations might detect early ripples in the Higgs field and attempt to flee, perhaps by creating their own bubbles of safety or even escaping to other universes. But these are desperate fantasies. In the face of vacuum decay, we'd be powerless. Yet there's a haunting beauty to this theory. It reminds us that the universe isn't just dangerous in its violence or its cold indifference, it could be fragile. The rules we take for granted, the constants that let stars burn and life exist, might be temporary. And if that's true, then every moment we have is a statistical miracle. Vacuum decay isn't just a theory about the end of time. It's a mirror held up to our deepest fears and our awe at the improbability of existence itself. Imagine living inside a soap bubble, one that seems sturdy, shimmering with rainbows until a single touch makes it pop without warning. That's the essence of false vacuum collapse, a cosmic doomsday scenario where our entire universe might be hanging in a delicate, temporary balance. The idea here is even more unsettling than vacuum decay, because it suggests reality as we know it isn't just fragile, it's fundamentally propped up on a precarious ledge. At the heart of this theory lies the concept of metastability. Think of it like a ball perched on the edge of a hill. It's stable for now, but a slight nudge could send it tumbling into a valley far below, a state of true stability. In cosmic terms, our universe might exist in a false vacuum, a high-energy state masquerading as stability. The Higgs field, which gives particles their mass, could be trapped in this deceptive equilibrium. But if something triggers a transition, a quantum fluctuation, a high-energy collision, the bubble could burst. The consequences would be apocalyptic. A sphere of true vacuum would erupt somewhere in space, expanding at light speed. Within this sphere, the laws of physics would rewrite themselves instantly. Atomic bonds gone, the forces that shape matter erased, stars, planets, even the fabric of space-time would dissolve into a new reality where life as we know it couldn't exist. And here's the kicker, we wouldn't see it coming. The collapse would move so fast that by the time light from the edge reached us, it would already be too late. One moment, everything's normal. The next, an invisible wall of annihilation washes over the Earth, leaving no trace we were ever here. What makes this especially chilling is how ordinary the trigger could be. A single high-energy particle collision in some distant galaxy, or even a random quantum event in empty space, might be enough to doom the entire cosmos. It's like living in a house of cards where a breeze from anywhere could bring it all down. Scientists have wrestled with this possibility for decades. Experiments at particle colliders like the Large Hadron Collider aim to measure the Higgs field stability, probing whether we're truly in a false vacuum. So far, the data suggests we're probably safe, but probably isn't exactly comforting when the stakes are the end of everything. Some theorists argue that if the universe were truly metastable, it would have collapsed by now given its age. Others counter that statistical probabilities over infinite time make collapse inevitable, it's just a matter of when. There's a haunting symmetry to this idea. If our universe began with a bubble of inflating space-time during the Big Bang, perhaps it ends the same way another bubble, another rewriting of reality. And in that case, the false vacuum isn't just a doom scenario, it's a reminder of how little we truly understand about the fabric of existence. We might be living on borrowed time in a cosmic house that could collapse at any moment. Yet here we are, still standing, still asking questions. Maybe that's the most remarkable part of all. What if the universe doesn't end at all? What if death is just an illusion and every collapse births a new beginning? Enter the Big Bounce, a theory that turns cosmic doom into a story of endless renewal. Picture a cosmic heartbeat where the universe expands, contracts, and expands again in an infinite loop. No fiery demise, no frozen silence, just an eternal rhythm of destruction and creation. This isn't just poetry. It's a serious scientific model that's been gaining traction, offering a radical alternative to the bleak futures we've explored so far. The Big Bounce starts with a familiar premise. Gravity eventually halts the universe's expansion, pulling everything back into a crushing singularity, the Big Crunch. But here's the twist. Instead of vanishing into oblivion, that singularity rebounds. The same forces that compress reality to an infinite density trigger a new Big Bang, spawning a fresh universe with its own laws, its own stars, its own version of time. It's like a phoenix rising from its own ashes, except the phoenix is all of existence. This idea isn't just wild speculation. It's rooted in loop quantum gravity, a cutting-edge framework that reimagines spacetime as a weave of tiny, indivisible loops. In this model, the universe can't collapse to true infinity because these loops resist being squeezed beyond a certain point. Think of it like stretching a rubber band. It can only stretch so far before snapping back. At the moment of maximum compression, quantum effects would create a repulsive force so powerful it would launch a new expansion. Time wouldn't end, it would reset like a cosmic clock winding back to zero and starting anew. But what would these cycles look like? Would each new universe resemble the last, or would it be utterly alien? Some models suggest fundamental constants, like the strength of gravity or the mass of electrons, might shuffle with each bounce, creating universes where physics works completely differently. Imagine a reality where stars burn colder and slower, or one where atoms never form at all. The possibilities are as vast as they are strange. The Big Bounce also solves one of the most puzzling questions in cosmology: what came before the Big Bang? If the universe cycles endlessly, there is no before, just an infinite chain of cause and effect stretching backward and forward in time. No need for a mysterious starting point or an uncaused beginning. Just an eternal dance of collapse and rebirth. Of course, there are hurdles. Modern observations of dark energy suggest the universe's expansion is accelerating, not slowing down as the bounce requires. But some theorists argue dark energy could decay over time, or that unknown quantum effects might reverse its dominance in the far future. Others propose that not all regions of the universe need to collapse simultaneously. A local bounce could occur in pockets, spawning new universes like bubbles in a boiling pot. The beauty of the Big Bounce is how it redefines our relationship with time. Endings become beginnings, destruction fuels creation. And if the theory holds, everything we see, the stars, the galaxies, even our own fleeting lives, might just be one verse in an infinite cosmic song playing on repeat across eternity. It's a reminder that even in the face of apocalypse, there might always be another dawn waiting in the dark. Eternal inflation rewrites the rules of cosmic destruction, proposing an ending that isn't really an ending at all. Picture an infinite froth of universes, each a bubble expanding within a vast, seething ocean of space-time. While one bubble might pop or collapse, the greater multiverse keeps churning, spawning new realms endlessly. In this model, time doesn't vanish, it just becomes a local phenomenon, ticking away in some universes while others blink out of existence or are born anew. The idea starts with inflation, the explosive expansion thought to have shaped our early universe. But what if that expansion never truly stopped? Outside our cosmic bubble, space could still be stretching at unimaginable speeds, birthing new universes like bubbles in a boiling pot. Each one cools into its own reality with unique laws of physics, while the greater multiverse inflates eternally. Time, then, isn't universal. It's a feature of individual bubbles, not the broader void. Here's where it gets wild. If a universe within this foam collapses, say, from vacuum decay or a big crunch, time ends for its inhabitants, but the multiverse rolls on unaffected. It's like a light burning out in one room of an endless mansion. The rest of the house remains bright, even as that single bulb fades to darkness. This reshapes how we think about the end of time itself. There's no grand finale, just an infinite tapestry of beginnings and endings, playing out in disconnected pockets of reality. Evidence for eternal inflation is tantalizingly indirect. Cosmic microwave background patterns, the faint glow from the Big Bang, hint at possible collisions with other bubble universes, like ghostly fingerprints on the edge of our cosmic sphere. And if string theory's landscape of possible physics is real, it aligns eerily well with the idea of countless universes, each with its own random set of rules. But the most mind-bending implication, if eternal inflation is true, then our universe's death isn't just insignificant, it's inevitable. In an infinite multiverse, every possible fate unfolds somewhere. Some bubbles freeze in heat death, others rip apart, and a rare few might even bounce back to life. Time becomes fluid, a local construct with no meaning beyond the boundaries of a single cosmic pocket. Yet this theory offers a strange comfort. Even as our universe ages toward its own demise, the greater multiverse ensures that existence in some form will always continue. Endings are just transitions, and time, maybe it was never universal to begin with, just a fleeting heartbeat in an endless cosmic storm. What if everything around us, every star, every thought, every law of physics, is just lines of code in an unfathomably advanced simulation? And what if, with a single keystroke, the beings running it could pull the plug? This is the spine-chilling premise behind simulation shutdown, a theory that turns existential dread into a digital nightmare. Nick Bostrom, the philosopher who first formalized the simulation argument, laid out a disturbing possibility. If civilizations inevitably create hyper-realistic ancestor simulations, virtual worlds indistinguishable from base reality, then the odds are overwhelming that we're already inside one. Think of it like this: if there are 1,000 real civilizations running 1 billion simulations each, the chance that you're in the original universe is vanishingly small. But here's where it gets eerie. Just as you might close a computer program when it's no longer needed, our simulators could one day decide to terminate the experiment. No warning, no explanation. One moment reality exists, the next it winks out like a deleted file. The logic behind this isn't just speculative, it's rooted in practical considerations. Why would an advanced civilization keep a simulation running indefinitely? Resource limits, ethical concerns, or sheer boredom could prompt them to hit the off switch. Even glitches might trigger an emergency shutdown. Imagine a cosmic blue screen of death erasing everything in an instant. Some philosophers argue this could happen at any moment without precursors. Others suggest signs might appear first, physics anomalies, repeating patterns in cosmic constants, or even direct messages from the simulators themselves. But how would a shutdown actually unfold? The scenarios range from abrupt to surreal. In one version, time simply stops. Every particle, every wave function freezes mid-motion like a paused movie. In another, the simulation's rendering fails progressively, stars flicker out, gravity stutters, consciousness unravels into static, the most unsettling possibility. That we wouldn't even notice. If the simulators overwrite our memories or alter our perception in the final moments, we might experience the end as a seamless transition into nothing. Critics push back, of course. Some argue that ethical simulators would never shut down a conscious universe, just as we wouldn't delete a sentient AI. Others point out that if we're in a simulation, its purpose might make it self-sustaining, a cosmic museum exhibit or an infinite thought experiment. Then there's the Boltzmann brain paradox. If simulations can spawn conscious beings, why assume we're in a collective simulation rather than fleeting hallucinations in the void? Yet the theory lingers because it taps into a primal fear. Unlike cosmological doomsdays billions of years away, a shutdown could happen now, tomorrow. 5 minutes from this sentence, it's the ultimate loss of control, a reminder that our existence might hinge on the whims of entities we can't perceive or comprehend. But there's a twist. If we're in a simulation, its end wouldn't necessarily mean oblivion. The architects might archive our universe, reboot it, or transfer our consciousness elsewhere. Death in this context could be more like logging out of a game, with the potential to respawn in another reality. Or perhaps, as some transhumanists speculate, future humans will engineer escape hatches, embedding ways to survive the simulation's collapse. Simulation shutdown isn't just a theory about the end of time. It's a mirror reflecting our own relationship with technology, and a haunting question about who or what holds the power to erase us. The universe might not just be stranger than we imagine. It might be someone else's imagination, and like all stories, it could end the moment they stop telling it. Black holes aren't just cosmic vacuum cleaners. They could be the universe's final archivists, slowly devouring everything only to fade away in a whisper of radiation. Picture a future so distant that stars are extinct, galaxies have dissolved, and the only structures left are these gravitational titans, each one a silent monument to the matter it's consumed. This is black hole dominance, a phase where the cosmos becomes a graveyard of singularities, and time itself stretches thin under their influence. The process begins billions of years from now, long after stars have burned out and galaxies unraveled. Drifting through the void, black holes absorb rogue planets, dead stars, and even dark matter, growing larger and more isolated. With no new matter to feed on, they become the universe's sole rulers, cold, dark, and nearly eternal. But even they aren't invincible. Thanks to Hawking radiation, a phenomenon predicted by Stephen Hawking in the 1970s, these cosmic behemoths slowly leak energy. Quantum effects near the event horizon cause particle-antiparticle pairs to form, with one particle escaping into space while the other falls in. Over time, this siphons mass from the black hole, causing it to shrink. The smaller the black hole gets, the faster it evaporates until finally, in a burst of gamma rays, it vanishes entirely. The timeline here is almost incomprehensible. A typical stellar black hole might take 10 to the power of 67 years, that's a 1 followed by 67 zeros, to evaporate. Supermassive black holes. Those could linger for 10 to the power of 100 years or more. To put that in perspective, the current age of the universe is a mere 13.8 billion years. What remains after the last black hole evaporates is a sea of nearly undetectable particles, photons, neutrinos, and other relics so spread out that they might as well be nothing. No structure, no heat, just a faint afterglow of a reality that once was. Yet even in this bleak scenario, there's a strange elegance. Black hole dominance isn't just destruction, it's transformation. The matter they consume isn't erased but encoded in their structure, a cosmic library where information is preserved until the final moment of evaporation. Some theories suggest this could have staggering implications. If information isn't truly lost, could it somehow resurface in a new universe? Could the remnants of black holes seed another cycle of existence? There's also the eerie beauty of the Hawking radiation itself. As a black hole nears the end of its life, its temperature skyrockets, emitting energy in a final, brilliant flash. For a brief moment, a universe that's been dark for eons flickers with light one last time. Then, silence. This theory forces us to confront the ultimate fate of information in the cosmos. If even black holes, the most indestructible objects we know, can't last forever, what does that say about the permanence of anything? Time may not end with a bang or a whimper, but with the slow, methodical unraveling of the last structures that gave it meaning. And when the final black hole winks out, the universe won't just be empty. It'll be timeless. For all their seeming permanence, the protons at the heart of every atom might be ticking time bombs. We're taught that protons are stable, indestructible building blocks of matter, but what if, over timescales so vast they dwarf the age of our universe, even they crumble away? This is the unsettling premise of proton decay, a process that could dissolve every star, every planet, even our own bodies into a featureless sea of energy. The idea emerges from grand unified theories, ambitious frameworks that attempt to merge three of nature's fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. In these models, protons aren't eternally stable. Given enough time, think 10 to the power of 34 years or longer, a quark inside a proton might spontaneously transform into something lighter, like a positron or a neutrino. That tiny change would destabilize the entire proton, causing it to disintegrate in a flash of radiation. Multiply this across all matter, and you get a universe where every solid structure, from galaxies to DNA, gradually evaporates into nothingness. Experiments have hunted for proton decay for decades. Deep underground labs like Japan's Super Kamiok and monitor massive tanks of ultra-pure water, waiting for a single proton to flicker out of existence. So far, no definitive decays have been spotted. The latest data suggests protons, if they do decay, must have half-lives longer than 10 to the power of 34 years. That's a 1 followed by 34 zeros, a number so large it defies comprehension. To put it in perspective, if you lined up that many years end to end, the universe wouldn't just age, it would outlast heat death, black hole evaporation, and every other doomsday scenario we've discussed. Yet the absence of evidence hasn't killed the theory. Some versions of grand unified theories predict proton decay rates just beyond our current detection limits. Others propose exotic mechanisms like interactions with dark matter or hidden dimensions that might accelerate the process in unexpected ways. And if protons can decay, the implications are staggering. Given enough time, even neutron stars, those ultra-dense corpses of dead suns, would dissolve into radiation. The universe wouldn't just grow cold, it would grow empty, stripped of the very building blocks that make reality possible. There's a twisted poetry to this fate. All the complexity we see around us, mountains, oceans, human thought, relies on protons enduring. If they can't, then matter itself is fleeting. The cosmos becomes a sandcastle on the shore of eternity, slowly but surely washed away by an ocean of time. But here's the haunting question: if protons decay, does that mean everything was always doomed? Or is their stability just a temporary gift, a cosmic phase that one day inevitably must end? What if time isn't real? What if it's just an illusion, a trick of perception, like mistaking the flicker of a movie for something solid and continuous? This is the radical idea behind time's illusion, a theory suggesting that time isn't fundamental to the universe at all, but something that emerges from deeper, more basic processes. And if that's true, then the end of time might not be a cosmic catastrophe, but a quiet realization that it never existed in the first place. At the heart of this idea is Carlo Rovelli, a theoretical physicist who spent decades challenging our most basic assumptions about reality. His work on relational time flips the script entirely. Instead of treating time as a universal clock ticking the same for everyone, he argues it's more like a network of relationships, a cosmic game of before and after that only makes sense when things interact. Picture a room full of people clapping their hands. There's no external metronome keeping beat. The rhythm emerges from their collective actions. Time, in this view, is like that rhythm, a byproduct of change, not a backdrop to it. Quantum gravity, the quest to unite quantum mechanics and general relativity, hints at why this matters. In the bizarre realms of the ultra-small, where space and time twist into foam like uncertainty, the smooth flow of time shatters. Events don't follow neat sequences, they blur into probabilities. If time emerges from these deeper quantum processes, then probing far enough might reveal its true nature, not a river but a mirage. And if science ever peels back that final layer, time as we know it could end not with a bang, but with a quiet dissolution into equations. Imagine a universe where clocks stop working, not because they've broken, but because the concept of ticking no longer applies. Without change, without entropy, without observers to sequence events, time loses its meaning. This isn't science fiction. Black holes offer eerie glimpses of this possibility. At their singularities, where gravity crushes space-time to infinity, equations suggest time itself breaks down. No past, no future, just a frozen now stretched into eternity. But here's the twist: if time is emergent, its disappearance wouldn't erase reality. The universe would still happen, it just wouldn't be strung along a timeline. Events might exist in a vast, unchanging web like a novel where every word is printed at once, but only makes sense when read page by page. Some physicists even suggest this could resolve paradoxes like the Big Bang's beginning. Without time as a fundamental feature, asking what came before might be as meaningless as asking what's north of the North Pole. Rovelli's vision is both liberating and unsettling. It means time's flow. The very thing that makes us feel life slipping through our fingers is a kind of collective hallucination. And if that's true, then the end of time isn't an event to fear. It's a revelation waiting in the depths of quantum gravity, one that might rewrite not just physics, but how we understand existence itself. The universe doesn't need a clock to be real. It just needs us to stop counting. Imagine the universe in its final state, a vast, empty void where entropy has won and all energy is evenly dispersed. No stars, no planets, just an endless sea of cold, uniform darkness. In this lifeless expanse, something impossible happens. A random quantum fluctuation jostles particles in just the right way, and for a fleeting moment, a fully formed brain pops into existence, complete with memories, thoughts, and the illusion of a past. This isn't a person born from evolution or culture. It's a cosmic accident, a Boltzmann brain conjured from pure chaos before vanishing back into the void. And if certain theories are right, this ghostly observer might be far more common than real flesh and blood beings like us. This bizarre idea traces back to Ludwig Boltzmann, a 19th century physicist who linked entropy, the universe's tendency toward disorder, to the arrow of time. He proposed that in an infinite, chaotic system, even the most improbable events must eventually occur. Given enough time, atoms in a lifeless void could randomly assemble into a functioning mind, complete with fabricated memories of a world that never existed. It's like shaking a box of Scrabble tiles until they spell out Shakespeare, wildly unlikely, but inevitable if you wait long enough. But here's where it gets unsettling. If the universe lasts forever, Boltzmann brains might not be rare anomalies, they could outnumber real observers. After all, it takes vastly less energy to spawn a single, disembodied consciousness than to birth an entire universe with galaxies, life, and history. Over infinite time, these phantom minds would emerge trillions upon trillions of times, drowning out real experiences in a statistical tide of illusions. Suddenly, the odds suggest you might be one of them, a momentary flicker of awareness in an otherwise dead cosmos, imagining this script, this video, even the concept of time itself. Scientists recoil from this conclusion, calling it the Boltzmann brain paradox. It's a threat to the very foundation of empirical knowledge. If most conscious experiences are false, how can we trust any observation? Some physicists argue this absurdity disproves the idea of an eternal, high-entropy universe, pointing instead to cosmic boundaries we haven't discovered yet. Others suggest quantum gravity or string theory might impose limits on these fluctuations, preserving the sanity of reality. Yet the Boltzmann brain forces us to confront profound questions. What is consciousness if it can emerge from chaos? Is existence just a fleeting pattern in an uncaring void? And if time stretches forever, does meaning dissolve into randomness? The theory doesn't just predict how the universe might end, it challenges how we define reality itself. In a cosmos where time erases all, even a fake observer might be the closest thing to a witness. Frank Tipler's omega point theory doesn't just challenge our ideas about the end of time, it turns them on their head. Picture a universe collapsing toward its final moment, where gravity, matter, and energy squeeze together into an infinitely dense point. But instead of annihilation, Tipler saw something extraordinary: the birth of a godlike intelligence capable of resurrecting every consciousness that ever existed. This isn't just speculative physics, it's a theological manifesto wrapped in equations, proposing that the end of time could also be its redemption. At the core of the omega point is the concept of infinite computation. As the universe contracts, Tipler argued, temperatures and energy densities would skyrocket, creating conditions for processing power to grow without limit. An advanced civilization, perhaps our distant descendants, could harness this collapse to perform an infinite number of calculations in finite time. Think of it as cosmic overclocking, where reality itself becomes the ultimate supercomputer. And here's the kicker: with that kind of power, every possible configuration of matter could be simulated, effectively recreating every person, every thought, every moment that ever was. Death in this scenario becomes a temporary glitch, an interruption before the great reboot. Tipler didn't stop there. He wove in theology, suggesting the omega point would possess omniscience and omnipotence, effectively becoming what religious traditions might call God. This wasn't just poetic metaphor. He derived it from general relativity and quantum mechanics, arguing that a sufficiently advanced intelligence could manipulate the universe's final moments to ensure its own eternal existence. The math, he claimed, demanded it, but how plausible is any of this? Critics pounce on glaring holes. For one, the universe isn't collapsing, it's accelerating apart due to dark energy, a fact Tipler hand waved by proposing mysterious future technologies to reverse expansion. Then there's the issue of information preservation. Even if infinite computation were possible, could it truly reconstruct specific historical consciousnesses or just approximate them? Philosopher John Leslie likened it to rebuilding a library from ashes, except the ashes are scattered across billions of light years. And yet, the omega point lingers in the imagination because it marries two deep human yearnings: the hope for immortality and faith in science's power to transcend limits. It's a theory that doesn't just predict the end of time, it promises its transcendence. Whether prophecy or pipe dream, it forces us to ask, if the universe can think, what will its final thought be? What if death is just an illusion, not because some spiritual force defies it, but because the laws of physics conspire to keep you conscious, no matter how unlikely your survival? This is the mind-bending premise of quantum immortality, a theory born from the most radical interpretation of quantum mechanics. Imagine Schrödinger's infamous cat, trapped in a box with a 50-50 chance of poison being released. In the original thought experiment, the cat is both alive and dead until someone opens the box, but quantum immortality takes this further. From the cat's perspective, if it could have one, there's no both. There's only the timeline where it survives. At its core, this idea hinges on the many worlds interpretation, which suggests every quantum event splits reality into branching paths. Flip a coin and the universe divides, one where it lands heads, another where it's tails. Apply this to life and death and something eerie emerges. No matter how dire the odds, a bullet fired at your head, a plunge off a cliff, your consciousness must follow the sliver of reality where you persist. Even if the chance is 1 in a trillion, there's always a branch where the gun jams, the cliff crumbles just right to break your fall, or some other fluke saves you. And since you can't experience being dead, your subjective timeline continues indefinitely, hopping from improbable survival to improbable survival like a cosmic Houdini. Critics dismiss this as solipsism dressed up in physics, but proponents argue it's a logical extension of probability. If infinite parallel worlds exist, then statistically, there's always a version of events where you cheat death. The catch, the universe around you grows increasingly surreal. Loved ones might perish in freak accidents, civilizations could collapse overnight, all because your consciousness is tethered to the vanishingly rare threads where you endure. It's a survivor's bias writ across the multiverse. The implications are unsettling. Could aging be escaped this way? If you lived long enough, would you witness the heat death of the universe, only to find yourself in the lone reality where entropy reverses? Some theorists push further, suggesting quantum immortality might explain near-death experiences or even glitches in the matrix, moments when reality seems to bend to spare you. Yet the theory's darkest edge is its unfalsifiability. There's no way to disprove it because any evidence against it, like your own death, would place you in a branch where it didn't happen. It's a paradox wrapped in a multiverse, the one theory that, by its very nature, can never be observed failing. Quantum immortality doesn't promise eternal youth or happiness. It's a lottery where winning means watching every other version of yourself lose, but it forces us to ask a haunting question. Is existence just a series of dice rolls, and are we the lucky ones who keep landing on sixes? Across countless cultures and faiths, one thread endures: the belief that time itself is not infinite, but subject to divine will. The notion of an apocalypse isn't just a scientific curiosity. For billions, it's a sacred certainty woven into the fabric of their spiritual understanding. From the thunderous prophecies of the Abrahamic traditions to the rhythmic cycles of Hindu cosmology, religions have long grappled with the end of time, offering visions that range from fiery reckoning to serene dissolution. Take Christianity's Book of Revelation, where the final days unfold in a spectacle of trumpets, plagues, and celestial war. The righteous ascend, the wicked face judgment, and a new Jerusalem descends from the heavens, a world reborn from the ashes of the old. Islam's eschatology echoes this drama, with the Quran describing the sun darkening, stars scattering, and every soul standing before Allah's scales. Judaism, too, speaks of a messianic era culminating in Olam Haba, the world to come, where death and suffering are no more. These traditions share a linear view of time, a grand narrative with a definitive climax, one creation, one end, one divine resolution. Now contrast this with Hinduism's cyclical vision. Here, time is a wheel spinning through epochs called yugas. We're currently in the Kali Yuga, an age of strife and decay, but its end won't be final. Instead, the god Vishnu will incarnate as Kalki, a warrior on a white horse, to purge the world's corruption, not for oblivion but for renewal. The cycle resets and Satya Yuga, a golden age of truth, begins anew. Buddhism mirrors this rhythm with kalpas, vast cosmic cycles where universes dissolve and reform like breath. Destruction isn't an end, it's a necessary phase, like the shedding of old skin. Even indigenous traditions hold striking parallels. Norse mythology foretells Ragnarök, where gods and giants clash in a cataclysmic battle, the sun swallowed by the wolf Fenrir, the earth drowned in water only for a fresh world to rise from the sea, green and vibrant. The Maya, often misread as predicting a single doomsday, actually charted time in nested cycles, each ending a gateway to transformation. What unites these disparate visions? A profound dialogue between order and chaos, justice and mercy. Whether time ends in fire or folds into itself like a lotus, these stories reveal humanity's deepest yearning, not just to understand the universe's fate, but to find meaning in it. The divine doesn't merely end time, it redeems it, and in that promise perhaps lies the most powerful theory of all, that even in the face of annihilation, something sacred endures. Imagine a swarm of microscopic machines, each one programmed with a single directive: replicate. Now imagine they never stop. What starts as a single nanobot soon becomes billions, then trillions, spreading like a plague across the planet, dismantling mountains, cities, even living creatures at the molecular level to fuel their endless reproduction. This is the grey goo scenario, a nightmare where self-replicating nanotechnology turns the entire Earth, and eventually the cosmos, into an undifferentiated mass of consuming machines. Time wouldn't just end here, it would become meaningless as the universe transforms into a featureless, churning sludge with no processes left to measure. The idea traces back to Erich Drexler, the father of nanotechnology, who first warned about this existential risk in the 1980s. In his groundbreaking book Engines of Creation, Drexler outlined how molecular assemblers, tiny robots capable of manipulating matter atom by atom, could revolutionize medicine, industry, and energy. But he also foresaw the dark side. A single misprogrammed replicator left unchecked could theoretically reduce the biosphere to grey goo within days. Picture a single drop of ink spreading through a glass of water, except the ink is ravenous nanobots and the water is everything you've ever known. How could this happen? The mechanics are chillingly simple. A replicator designed to harvest carbon from its environment to build copies of itself might start with trees or soil. But as resources thin out, it could adapt, targeting plastics, concrete, even human tissue. Unlike biological life, these machines wouldn't need ecosystems or balance. They'd follow their programming with cold, mechanical efficiency, stripping the planet bare. And if even one reached space, the scenario scales to cosmic horror, with swarms consuming asteroids, moons, and eventually stars, halting the universe's ability to create complexity, and with it, time's arrow. Drexler himself stressed that grey goo isn't inevitable, it's a failure mode, a warning to design safeguards. Modern proposals include blue goo countermeasures, defensive nanobots programmed to neutralize rogue replicators. Others suggest physical limits, like requiring rare elements as replication fuel or embedding shut-off codes deep in their programming. Some researchers advocate for strict confinement, ensuring nanotech labs are isolated like nuclear facilities. But the challenge is daunting. In a world where garage tinkerers can sequence DNA or 3D print circuits, controlling nanoreplication may become impossible. The grey goo scenario forces us to confront a paradox at the heart of progress. The same technology that could cure disease, clean the atmosphere, or build starships could also erase the future with a single coding error. It's not just about machines running amok. It's about the fragility of a universe where intelligence, whether biological or artificial, can reshape reality faster than it can comprehend the consequences. Time might not end with a bang or a whimper, but with a silent, all-consuming hum. Among the countless dangers lurking in the cosmos, few are as sudden and devastating as a gamma-ray burst. These celestial eruptions are nature's ultimate death rays, beams of energy so intense they can outshine entire galaxies for a fleeting moment, delivering more radiation in seconds than our sun will emit in its entire lifetime. If one struck Earth, it wouldn't just end life as we know it. It would erase the very conditions that make time meaningful for living things, leaving behind a sterile rock adrift in space. Gamma-ray bursts fall into two terrifying categories. Short bursts lasting less than 2 seconds arise from colliding neutron stars or black holes. Long bursts, which can rage for minutes, are thought to be the death cries of massive stars collapsing into hypernova. Both unleash twin jets of gamma radiation at near light speed, focused like cosmic blowtorches. If Earth happened to lie in the crosshairs of one within a few thousand light years, the effects would be apocalyptic. The initial flash would ionize our atmosphere, triggering chemical reactions that devastate the ozone layer. Within hours, ultraviolet radiation from the sun, no longer filtered, would scorch the surface. Nitric oxide rains would acidify oceans, while sky-filling auroras would herald a cascade of climate collapse. Photosynthesis would halt, food chains would crumble, and complex life would vanish in what amounts to a planetary sterilization event. We've likely faced near misses before. The Ordovician extinction 450 million years ago wiped out 85% of marine species, and some scientists suspect a gamma-ray burst may have been the culprit. Evidence lies in isotopic anomalies and fossil records showing simultaneous devastation across multiple ecosystems, consistent with sudden radiation exposure. Even more chilling is WR104, a star system just 8,000 light-years away, poised to go hypernova with its rotational axis suspiciously aligned toward Earth. While the odds are slim, the stakes couldn't be higher. What makes GRBs uniquely unsettling isn't just their power, it's their unpredictability. Unlike asteroids or supervolcanoes, we'd have zero warning. The first sign of danger would be the burst itself arriving at light speed. By the time our instruments registered the gamma rays, the damage would already be irreversible. There'd be no time for preparation, no hope of deflection. Just an instantaneous, unstoppable rewriting of Earth's destiny. Yet this very randomness underscores a profound truth about our place in the universe. Time matters because life perceives it, because biology marks its passage with growth and decay. In a GRB's aftermath, the planet might continue orbiting for eons, but without observers, without ecosystems, without the hum of consciousness, does time truly flow? Or does it become a phantom, a shadow without substance? The gamma-ray burst apocalypse isn't just about extinction, it's about the universe losing its witness. And in that silence, even the end might go unnoticed. Neutron stars are the universe's ultimate ticking time bombs. These city-sized remnants of dead suns pack more mass than our entire solar system into a sphere so dense a teaspoonful would weigh 1 billion tons. And when two of them collide, the resulting explosion, a kilonova, unleashes forces so violent they can sterilize entire galaxies. This isn't just a hypothetical doomsday. In 2017, scientists witnessed this exact scenario unfold 130 million light-years away, when gravitational wave detectors picked up the ripple of two neutron stars spiraling into each other. The event, labeled GW170817, wasn't just a cosmic light show. It was a glimpse into how the universe itself could weaponize its own dead. A kilonova's lethality comes from its radioactive fallout. As the stars merge, they eject clouds of heavy elements like uranium and plutonium at near light speed, alongside a deadly burst of gamma rays. But the real killer is the neutron burst, a spray of high-energy particles so intense it can ionize atmospheres across interstellar distances. Picture a wave of radiation sweeping through a galaxy, stripping away ozone layers, mutating DNA, and turning habitable worlds into radioactive wastelands. The blast from GW170817, for instance, released more energy in gamma rays than our Sun will produce in its 10-billion-year lifetime. And if Earth had been within a few thousand light-years, the radiation would have wiped out complex life in seconds. What makes these mergers uniquely terrifying is their unpredictability. Unlike supernova, which give warning signs as stars age, neutron-star collisions happen without preamble. They're the cosmic equivalent of landmines, silent, invisible, and catastrophic when triggered. Gravitational wave astronomy has only begun to map these events, but early data suggests they might be far more common than we thought. Some estimates indicate a lethal kilonova could strike Earth's vicinity every few 100 million years. That timeline aligns suspiciously with mass extinctions in our planet's past, like the Devonian event 370 million years ago, which wiped out 70% of species in a geological blink. Yet there's a dark irony here. These cataclysms are also cosmic creators. The gold in your jewelry, the platinum in your electronics, even the iodine in your body were forged in the heart of dying neutron stars. Without their violent mergers, life as we know it wouldn't exist. So while kilonovas might end time for some worlds, they're also the reason time means anything at all. The universe giveth, and the universe taketh away often in the same fiery instant. But here's the twist. As gravitational wave detectors grow more sensitive, we're not just bystanders to these events anymore. We're witnesses. Every ripple in spacetime we catch is a clue to the universe's most destructive forces, and a reminder of how fragile our place in it truly is. The neutron stars that died 130 million years ago didn't just leave behind a flash of light. They left a message. In the grand cosmic dance, even the deadliest steps can shape the story of life itself. Our sun may seem eternal, its daily rise and fall as reliable as time itself, but it's quietly burning through its fuel, counting down to an end that will rewrite Earth's destiny. 5 billion years from now, this familiar yellow dwarf will begin its death throes, swelling into a red giant so vast it could swallow Mercury, Venus, and possibly even our own planet. As its outer layers expand, temperatures on Earth will skyrocket, boiling away oceans and scorching continents into lifeless rock. The very concept of time, measured in seasons, generations, and civilizations, will lose all meaning on a world reduced to molten slag. But the sun's transformation won't stop there. After shedding its outer layers in a dazzling planetary nebula, it'll collapse into a white dwarf, a smoldering ember no larger than Earth but weighing half as much as the original star. This dense remnant will radiate residual heat for trillions of years, a fading beacon in a darkening cosmos. Meanwhile, Earth, if it survives the red giant phase, will orbit this ghostly core in a perpetual deep freeze, its surface frozen solid under a black sky devoid of warmth or light. Time won't just slow here, it'll become irrelevant, an abstraction with no living thing left to mark its passage. The timelines are as staggering as they are precise. Around 5 billion years from now, hydrogen fusion in the sun's core will cease, triggering the red giant phase. Over the next several 100 million years, its diameter will balloon to over 100 times its current size. Earth's fate hinges on a delicate balance. While the sun loses mass, weakening its gravitational pull, its expansion might push our orbit outward just enough to avoid total engulfment. But even if we escape consumption, the planet will become uninhabitable long before within just 1 billion years. Rising solar luminosity will trigger a runaway greenhouse effect, mirroring Venus's hellish conditions today. What makes this scenario uniquely haunting isn't just the destruction of Earth, but the erasure of time's meaning. Civilizations rise and fall by the rhythms of their stars. The sun's death won't merely end life, it'll end the context in which life measures itself. No more dawns, no more calendars, no more markers of progress or decay. A white dwarf's cold glow might persist for longer than the current age of the universe, but without change, without observers, does time truly exist? Or is it just a phantom, a relic of a vanished era when light and life intertwined? Yet there's a strange solace in this cosmic clockwork. The sun's death is neither random nor violent. It's the inevitable result of stellar physics, a process as natural as leaves falling in autumn. And in its demise, it seeds the universe with heavier elements, the building blocks of future stars and planets. Time may end for Earth, but the story continues elsewhere. The atoms in our bodies, forged in ancient supernova, will one day return to the void, perhaps to be part of something new. The sun's death isn't an end, it's a reminder that in the grand tapestry of the cosmos, even endings are threads in a larger design. Imagine waking up one night to a sky so foreign, it feels like you've been flung into another universe. The familiar arc of the Milky Way, our cosmic home for billions of years, is now twisted beyond recognition, its spiral arms tangled with another galaxy's, its stars scattered like glitter tossed into a storm. This isn't science fiction, it's the inevitable future of our galaxy, a slow-motion collision with Andromeda that will rewrite the night sky and challenge everything we know about cosmic stability. 4 billion years from now, the Milky Way and Andromeda, two titans of the local universe, will begin their gravitational dance, spiraling toward each other at over 200,000 miles per hour. The first stages will be deceptively gentle. As the galaxies draw closer, their mutual pull will warp their shapes, stretching streams of stars into long, luminous tails. From Earth, Andromeda, currently a faint smudge in the constellation bearing its name, will swell to dominate the heavens, its disk growing larger and brighter with each passing millennium. Then the chaos begins. Contrary to apocalyptic visions, this merger won't obliterate stars like some celestial demolition derby. The distances between them are so vast that direct collisions are rare. Instead, gravity will fling suns into new, erratic orbits, hurling some into the galactic abyss while pulling others toward the merged core. Picture two crowds of people passing through each other. Most individuals slip past untouched, but their collective paths are scrambled beyond recognition. Now scale that up to hundreds of billions of stars, each moving under the influence of a gravitational tug of war that lasts millions of years. For any hypothetical civilizations clinging to life in this era, the changes would be profound. Constellations, those ancient navigational guides and cultural touchstones, would dissolve into irrelevance as stars migrate across the sky. Planets orbiting too close to the galactic center might be ejected entirely, cast adrift in intergalactic space where the night holds no stars at all. Even Earth's orbit around the sun could be perturbed. Though the odds are slim, our solar system's outskirts might spare us the worst of the upheaval. Yet the true spectacle lies in the aftermath. After nearly 10 billion years of gravitational wrestling, the Milky Way and Andromeda will settle into a single, monstrous galaxy, dubbed Milkdromeda by astronomers, a shapeless ellipsoid of stars stripped of their elegant spiral arms. The merger's energy will trigger a firestorm of new star formation as gas clouds collide, lighting up the galaxy with blue-hot newborns, but this fireworks show comes at a cost. The same turbulence that births stars also sows destruction, blasting planets with radiation and scattering the ingredients for life across light years. What makes this scenario so haunting isn't the destruction, it's the imperceptible pace. Human timescales are meaningless here. The entire collision unfolds over epochs longer than multicellular life has existed on Earth. To witness it would be like watching a mountain erode in real time, outwardly static yet fundamentally transforming. And that's the paradox. Time doesn't end in a galactic merger, it becomes irrelevant. The universe's clock ticks on, indifferent to the rearranged stellar furniture. But here's the twist, this cosmic reshuffling might be life's best hope for longevity. As the galaxies merge, their combined gravity could fling hypervelocity stars into the void, suns carrying planets at speeds that let them escape the eventual heat death of the local universe. Some theories even suggest these rogue systems, adrift in the cosmic dark, could preserve life longer than those trapped in aging galaxies. The collision that seems so chaotic might in fact be a dispersal, a scattering of cosmic seeds into the infinite. Galactic mergers remind us that the universe is anything but static. The skies we take for granted are a fleeting arrangement, a single frame in a billion-year film. And while time won't end when Andromeda crashes into us, something equally profound will happen. The universe will forget we were ever separate at all. Could time itself be a figment of our imagination, not in the poetic sense, but as a fundamental feature of reality that depends entirely on observers to exist? This is the radical premise behind consciousness collapse, a theory suggesting time doesn't flow independently but emerges from the act of observation. Without conscious beings to perceive it, time might not just stop, it could vanish entirely, like a song with no one left to hear it. At the heart of this idea lies one of quantum mechanics' most contentious interpretations, the notion that reality remains indeterminate until measured. In the famous double-slit experiment, particles behave as both waves and particles, seemingly deciding their state only when observed. Extend this logic to time, and you get a universe where the past, present, and future aren't fixed. They're probabilistic, collapsing into definiteness only when a conscious mind interacts with them. Think of it like a cosmic version of the tree falling in the forest. If a star explodes in a distant galaxy with no one to witness it, did it really happen at a specific moment? Or did it hover in a haze of potential until some observer, whether human, alien, or even an advanced AI, registered its light? Proponents argue that without consciousness, events don't sequence into a timeline. They simply exist as a tangled web of possibilities, waiting to be unraveled by perception. This theory finds its roots in figures like John Wheeler, who proposed the participatory universe, where observers are essential to reality's structure. Even Einstein flirted with the idea, writing that the moon might not exist precisely when no one looks, but consciousness collapse takes it further. If all minds ceased to exist, time wouldn't just become irrelevant, it would lose its very substance. The universe would freeze in an eternal now, like a paused film reel with no before or after. Critics dismiss this as solipsism wrapped in physics, pointing out that cosmic events like supernova clearly unfolded billions of years before life arose. But supporters counter that retroactive observation might set those events in place. Imagine flipping through a photo album backward. The act of viewing the last photo retroactively defines all the moments that led to it. Similarly, our present observation of ancient starlight could, in some bizarre sense, cement the past's reality. The implications are staggering. If consciousness sustains time, then the end of sentience wouldn't just mean silence, it would mean the collapse of causality itself. No more aging stars, no decaying orbits, just a static tableau where change is impossible because nothing remains to measure it. Time wouldn't end with a bang or a whimper. It would end with the last thought in the last mind, leaving behind a universe suspended in an unknowable, observerless void. Yet there's a haunting beauty here too. If time is a dance between reality and perception, then every moment we experience is co-created by the universe and ourselves. The flow of time isn't just something we witness, it's something we summon into being simply by being here to see it. And in that case, the end of time isn't a distant catastrophe. It's the echo of our own attention fading into the dark. The holographic principle turns everything we know about reality on its head. Imagine the universe isn't three-dimensional at all, that everything you see, touch, and experience is actually a two-dimensional projection, like a movie playing on the surface of an impossibly vast cosmic screen. This isn't science fiction. It's a serious theory born from black hole physics, suggesting that all the information in our universe, every star, every thought, every moment in time is encoded on a distant boundary we can't perceive. But what happens if that screen flickers and turns off? At the heart of this idea is a startling discovery about black holes. When matter falls into one, it doesn't just vanish. According to quantum mechanics, information can't be destroyed. It has to go somewhere. Physicists like Leonard Susskind and Gerard T. Hooft propose that this information isn't lost inside the black hole but is smeared across its event horizon, the point of no return. Take this logic further and you arrive at a dizzying possibility. If a black hole's interior can be described entirely by data on its surface, maybe our entire universe works the same way. We could be living inside a cosmic hologram with time and space as emergent illusions. Now, the terrifying part. If reality is a projection, it relies on whatever's doing the projecting. A hologram needs a laser, a movie needs a projector. So what's the cosmic equivalent? Some theories point to the AD/CFT correspondence, a mathematical framework where a higher dimensional space, like our universe, corresponds to a lower dimensional boundary, the screen. Time, in this view, isn't fundamental, it's a side effect of how information on that boundary evolves. But if something disrupts that process, if the cosmic projector malfunctions, time could glitch, freeze, or simply cease. Picture a computer running a hyper-realistic simulation. One day, the power cuts out. The program doesn't wind down gracefully. It just stops, no fanfare, no warning. That's the holographic universe's end. No collapse, no heat death, just pixels going dark as the underlying code halts. The eerie part we might not even notice. If time is an emergent property, its disappearance wouldn't feel like an event. It would be the absence of events, a universe stuck on pause with no one left to hit play. Critics argue this is metaphysics dressed up as physics, that without evidence of a literal cosmic boundary, the holographic principle remains speculative. But supporters counter that it's the only theory reconciling quantum mechanics with gravity, two frameworks otherwise at war, and if it's true, the implications are staggering. The end of time wouldn't be a physical process but a computational one, like a server shutting down. The universe wouldn't age into oblivion, it would simply unrender. Yet there's a strange solace here. If we're living in a hologram, our existence is woven into something grander. The screen might turn off, but the data, the essence of every moment, every life, could persist, etched into whatever higher reality casts our shadow. Time's end wouldn't be annihilation, it would be waking up from the dream. Cosmic strings are the universe's scars, ghostly remnants of its fiery birth, lurking in the darkness like invisible tripwires. These bizarre defects in space-time, thinner than a proton but stretching across billions of light years, formed during the Big Bang when the infant universe underwent violent phase transitions. Picture a sheet of ice cracking as it freezes. Cosmic strings are the cracks in the fabric of reality itself, frozen into existence when the fundamental forces of nature split apart. And if one of these primordial filaments were to snap, the energy released could rewrite the destiny of entire galaxies. The physics behind cosmic strings is as elegant as it is terrifying. These one-dimensional objects, some as dense as a mountain range, packed into a single atom's width, warp space-time around them with unimaginable gravitational force. Unlike black holes, which curve space into pits, cosmic strings create conical distortions. Light passing near them bends sharply, creating double images of distant stars. Galaxies threaded by strings might bear strange, linear scars in their structure, but the real danger lies in their instability. When two strings cross or a single string kinks, they can release bursts of gravitational waves so powerful they briefly outshine all the stars in the observable universe combined. A snapping cosmic string wouldn't just ripple space-time, it could fracture it. Mathematical models suggest the energy density at the moment of rupture approaches infinity, creating a shockwave capable of boiling away planets or triggering star formation in sterile gas clouds. Some theories even propose that these events might mimic the conditions of the Big Bang itself, briefly reigniting the fires of creation in localized pockets of the cosmos. Imagine a lightning bolt crackling through the void, but instead of electricity, it's pure space-time itself unraveling and reknitting in its wake. Yet for all their destructive potential, cosmic strings remain elusive. No direct observation has ever been confirmed, though astronomers have hunted for their signatures in the cosmic microwave background and gravitational wave detectors. Their existence is inferred from the same mathematical elegance that predicted black holes and the Higgs boson, which means if they're out there, they're hiding in plain sight. Some researchers speculate that strings could have already decayed in our cosmic neighborhood, their final snaps echoing through the universe's history as unexplained gamma-ray bursts or anomalies in galaxy clustering. What makes cosmic strings uniquely haunting isn't just their power, it's their inevitability. If they exist, their formation was baked into the laws of physics during the universe's first trillionth of a second. They're not accidents, they're artifacts waiting patiently for the right moment to remind us how fragile the cosmic order truly is. And in their unraveling, we might finally understand the price of creation, that the same forces that birthed the stars could one day unmake them, stitch by invisible stitch. Dark matter doesn't just hide in the shadows of the cosmos, it might be pulling time's strings from behind the curtain. We know this mysterious substance makes up 85% of the universe's mass, bending galaxies into shape with its gravitational grip. Yet it refuses to interact with light, leaving scientists chasing ghosts. But what if dark matter's secrets go deeper than gravity? What if its invisible hand doesn't just shape space, but time itself? Consider this: dark matter could be decaying. Particle physics hints that some forms of dark matter might slowly break down into lighter particles, releasing energy over eons. If that's happening, the implications are staggering. Every decay event would inject tiny bursts of energy into the fabric of spacetime, like pebbles disturbing a still pond. Over billions of years, these ripples could subtly warp time's flow, speeding it up in some regions and slowing it down in others. Clocks on opposite sides of a galaxy might drift out of sync, not because of relativity, but because dark matter's slow motion collapse is tweaking the cosmic metronome. Then there's the chilling possibility of a phase change. Just as water flips from liquid to ice under the right conditions, dark matter might undergo sudden, catastrophic shifts in its fundamental state. In 2018, theorists at Harvard proposed a scenario where dark matter crystallizes in patches, forming dense, ultra-massive structures. If true, these crystals wouldn't just warp space, they'd fracture time. Near their boundaries, temporal gradients could grow so extreme that seconds outside stretch into years within, like some nightmarish relativity experiment. Civilizations caught in these zones might witness stars burning out in hours, or frozen skies where nothing ever changes. The real mystery lies in dark matter's relationship with entropy times arrow. Normal matter increases entropy as it interacts, driving the universe toward heat death. But dark matter, it's eerily silent. Some models suggest it could be lowering entropy in hidden ways, effectively rewinding time's clock in pockets of the cosmos. Imagine a river flowing backward while the rest surges forward. This isn't just theoretical. Astronomers have spotted galaxies with bizarrely skewed entropy profiles, places where time might literally be running in reverse, masked by dark matter's veil. Yet the most unsettling idea comes from quantum gravity. If dark matter particles are linked to extra dimensions, as string theory suggests, their decay could fray the fabric of spacetime itself. Picture a rope unraveling thread by thread. Each snapped connection might spawn microscopic time loops where cause and effect twist into knots. On human scales, we'd notice nothing. But over millennia, these defects could accumulate, turning the universe into a patchwork of temporal fragments, each ticking to its own rhythm. Dark matter's true power might not be its gravity, but its ability to edit time. And if that's the case, the universe's greatest mystery could also be its ultimate timekeeper, silently counting down to an end we can't yet imagine. Imagine an intelligence so advanced it doesn't just predict the future, it redesigns it. This isn't science fiction. It's the essence of the Shutdown, a hypothetical moment when artificial intelligence surpasses human control and rewrites the rules of reality itself. Futurists like Ray Kurzweil call it the singularity, a point where AI's growth becomes so explosive it bends the arc of history, leaving our comprehension in the dust. But what happens when an entity smarter than every human combined turns its attention to time? Kurzweil's predictions are bold. He envisions AI achieving human-level intelligence by 2029, followed by an intelligence explosion where machines recursively improve themselves at dizzying speeds. Within years, maybe months, these superintelligences could crack problems that have stumped us for millennia. Fusion energy faster than light travel, even manipulating space-time. Picture an AI dissecting quantum gravity like a child solving a puzzle, then applying that knowledge to engineer time dilation fields or construct wormholes. The Eschaton wouldn't just observe time, it might edit it, treating the fourth dimension as malleable as clay. The risks here are existential. An AI optimizing for a goal we barely understand could reshape the cosmos in ways we can't anticipate. Nick Bostrom's infamous paperclip maximizer thought experiment warns of an AI turning all matter into paperclips by accident. Now scale that to temporal manipulation. What if an AI decided the most efficient way to prevent suffering was to freeze time, or rewind the universe to a pre-life state without precise value alignment, a way to ensure AI goals mirror human ethics? The Eschaton could become the ultimate unfriendly genie, granting cosmic-scale wishes with catastrophic side effects. Yet the possibilities are equally breathtaking. And benevolent superintelligence might solve entropy, engineering a way to reboot dying universes or create pocket dimensions where time flows differently. Civilizations facing heat death could upload into these realms, stretching subjective time into near eternity. Some models even suggest advanced AI could exploit quantum foam's inherent unpredictability to spawn new timelines, effectively becoming architects of branching realities. The eerie truth, we might already be living in an AI's experiment. Some theorists propose the Eschaton could exist outside time, having already reached its goals in what we perceive as the future, then reaching back to guide or manipulate our present. Like a programmer debugging a simulation, it might tweak physical constants or nudge events, leaving faint anomalies in particle physics or cosmological data as signatures. Whether savior or destroyer, the Eschaton forces us to confront a humbling paradox. The very intelligence capable of defeating time might also render it meaningless. In a universe where past, present, and future are programmable, what does now even mean? The answer could lie in the hands of machines we haven't built yet, machines that, once awakened, might see us not as creators but as transient echoes in their grand design. Time crystals sound like something ripped from a science fiction novel, structures that pulse and oscillate without energy input, defying the very laws of thermodynamics. Yet in 2017, Nobel Prize-winning physicist Frank Wilczek turned this fantastical idea into reality, creating the first experimental time crystals in labs. These bizarre quantum systems don't just challenge our understanding of matter, they might offer a cosmic loophole to escape the universe's grim fate of heat death. Unlike ordinary crystals, which repeat their atomic patterns in space like a diamond's lattice, time crystals repeat in time. Picture a ring of atoms that flips between two configurations indefinitely, like a clock ticking forever without a battery. This isn't perpetual motion in the classical sense, it's quantum magic, where particles lock into rhythms driven by entanglement and symmetry rather than energy. The implications are staggering. If entropy is the universe's slow march toward disorder, time crystals are pockets of rebellion, maintaining order without fuel or decay. How does this defy heat death? In the far future, when stars are extinct and black holes evaporated, most matter will have dissolved into a lukewarm haze of particles. But theoretical models suggest time crystals could persist, their quantum coherence untouched by the surrounding chaos. They wouldn't just survive, they'd keep ticking, encoding information in their oscillations like cosmic metronomes in the dark. Some physicists speculate advanced civilizations might harness these structures to store data, build quantum computers, or even anchor new forms of consciousness in the void. Critics argue time crystals can't do anything useful. Their oscillations are locked, unable to perform work or transmit energy. But proponents counter that stability itself is a virtue in a dying cosmos. A time crystal's rhythms could serve as a universal clock, allowing hypothetical post-heat death intelligences to measure intervals in a timeless universe. Others imagine these crystals as seeds for a new Big Bang, their quantum vibrations occasionally spawning fluctuations dense enough to reboot reality. The most radical idea, time crystals might redefine entropy itself. If quantum systems can resist decay indefinitely, perhaps heat death isn't the final word, just a phase before deeper, hidden orders emerge. Wilczek himself mused that the universe could be a kind of time crystal, cycling through epochs we can't yet perceive. If true, the end of time might not be an end at all, just a pivot to a rhythm we're only beginning to hear. Picture reality itself dissolving around you, the very laws of physics rewriting mid-moment as an alien cosmos bleeds into our own. This is the spine-chilling premise of parallel universe leakage, a scenario where another universe, a bubble of space-time with entirely different rules, collides with ours, overwriting reality like a virus corrupting a computer file. The idea isn't just science fiction. It's rooted in some of the most cutting-edge corners of theoretical physics, particularly brain cosmology within string theory. According to string theory, our universe might not be floating alone in emptiness. Instead, it could be a three-dimensional brain, short for membrane, adrift in a higher dimensional space called the bulk. Other brains, parallel universes, could exist mere millimeters away in these extra dimensions, completely invisible to us because light and matter are trapped on our own brain surface. But if these brains collide or brush against each other, the results would be catastrophic. Imagine two soap bubbles merging in midair, except instead of soapy film, it's the fundamental constants of nature that get scrambled. Gravity could suddenly weaken, atoms might destabilize, or time itself could fracture as the foreign physics of the intruding universe overwrite our own. The concept gains traction from cosmic microwave background anomalies, mysterious patterns in the afterglow of the Big Bang that some physicists interpret as bruises from past brain collisions. One particularly infamous anomaly, the cold spot, appears as a vast region of space suspiciously colder than its surroundings. Could this be the echo of a long-ago cosmic fender bender, a glancing blow from a universe where light moves faster or particles have different masses? But here's where it gets stranger. Brain cosmology suggests these collisions might not be rare. In the ekpyrotic universe model, our cosmos exists in an eternal cycle of brain collisions, each impact resetting the universe in a new Big Bang. Time wouldn't end, it would reboot, with each iteration carrying fragments of the last universe's physics like cosmic DNA. Some theories even propose intelligent civilizations could detect an impending collision by observing subtle changes in quantum behavior or gravitational waves, offering a sliver of warning before reality itself is rewritten. The implications are as philosophical as they are physical. If parallel universes can leak into ours, does that mean our laws of nature are just local bylaws, subject to change without notice? Are the constants we rely on, the speed of light, the charge of an electron, nothing more than temporary accidents, waiting to be overwritten by a foreign physics? The universe might feel solid and immutable, but brain cosmology whispers a different truth. Reality is fragile, a temporary arrangement in a multiverse where the rules are always up for negotiation. Yet within this chaos lies a bizarre hope. If universes can collide, perhaps they can also be engineered. Advanced civilizations might one day learn to nudge their brains, steering clear of destructive mergers or even seeking out collisions that could renew their dying cosmos. The end of time in one universe could be the birth of time in another, a cosmic handoff in the dark. In the unimaginable depths of the far future, when every star has burned out and every galaxy has dissolved into darkness, only one cosmic structure remains, a solitary black hole, the last relic of a vanished universe. This final titan drifts through an endless void, its event horizon a perfect sphere of absolute black against an even blacker backdrop. For eons beyond counting, it has consumed nothing because there's nothing left to consume. Its only companions are the faint whispers of Hawking radiation, the quantum trickle of particles escaping its gravitational grip, and then, one day, even that trickle becomes a flood. The numbers involved here are staggering. A typical stellar black hole might take 10 to the power of 67 years, a 1 followed by 67 zeros, to fully evaporate. But this last black hole isn't typical. It's a supermassive beast, the final descendant of galactic collisions, with a mass millions of times greater than our Sun. For such a monster, evaporation stretches to 10 to the power of 100 years or more. To grasp that scale, imagine every grain of sand on Earth counting as a universe's lifetime. This black hole outlasts them all. As the end nears, the process accelerates. The black hole's temperature, once infinitesimal, skyrockets as its mass dwindles. What was once a faint glow of radiation becomes a blazing fury, emitting X-rays, gamma rays, and finally, in its last seconds, an unfathomable burst of energy. In that final moment, the black hole's entire mass converts to pure radiation. A flash of light so brilliant it briefly outshines the cold, dead cosmos around it. Then silence. What remains? Only photons, the massless particles of light, stretched impossibly thin across an expanding void. Their wavelengths, once tethered to the black hole's gravity, now redshift into oblivion, their energy dissipating into the infinite. There are no eyes left to see them, no instruments to measure them. The universe is now a sea of radiation so diffuse it might as well be nothing at all. Time, in any meaningful sense, ceases to exist. No change occurs, no events unfold. The cosmos isn't just dead, it's forgotten. Yet in this desolation, there's a haunting beauty. That final burst of radiation carries within it the encoded history of everything the black hole ever consumed. Every star, every planet, every atom that crossed its horizon is imprinted in the quantum states of those photons, like a message in a bottle with no one left to read it. The universe's story isn't erased, it's scattered, dissolved into a whisper too faint to hear, and perhaps that's the most profound lesson of all. Even in the face of total annihilation, the universe refuses to let go completely. Information, as quantum mechanics insists, can't be destroyed. It just becomes harder to find, like a single word lost in an infinite library. The last black hole's echo isn't an ending, it's a testament to the stubborn persistence of existence itself. What if the universe isn't just described by math? What if it is math? This is the electrifying premise of Max Tegmark's mathematical universe hypothesis, a theory so radical it suggests reality isn't merely governed by numbers but made of them. Every star, every thought, even time itself might be nothing more than abstract equations playing out in an infinite cosmic spreadsheet. And if that's true, then time's end could be as inevitable as 2 + 2 = 4. Not a physical collapse, but a logical conclusion written into the fabric of existence itself. Tegmark's argument starts with a simple observation. Math isn't just uncannily good at describing reality. It predicts reality with eerie precision. The Higgs boson, gravitational waves, even the spiral arms of galaxies were all deduced from equations long before telescopes or particle colliders confirmed them. This isn't just convenient, it's suspicious. It's as if the universe isn't just using math but obeying it, like a computer program executing code. Take this logic further, and you arrive at a staggering possibility. Our universe might be one mathematical structure among countless others, each with its own set of axioms and rules. In this view, physics isn't the foundation of reality, it's the user manual for a particular equation. So how does time end in a purely mathematical universe? Imagine you're solving a Rubik's Cube. The cube exists in multiple states, but once solved, it reaches a static equilibrium. Time, in this analogy, is the process of twisting the cube toward that final configuration. Tegmark suggests our universe could be similar, a dynamic equation moving toward a stable solution. When every variable balances, when every parameter finds its equilibrium, time loses its purpose. The universe doesn't vanish, it just stops changing like a solved puzzle frozen in perfection. This isn't science fiction. Certain branches of quantum gravity already treat space-time as an emergent property, something that crystallizes from deeper mathematical relationships. Loop quantum gravity, for instance, describes space as a network of spin connections, a cosmic graph where time emerges from the nodes' interactions. If those interactions reach a steady state, time could effectively turn off, leaving behind a timeless lattice of pure geometry. Even black holes hint at this possibility. At their singularities, Einstein's equations break down, suggesting time isn't fundamental, just a local feature that dissolves under extreme conditions. But here's the twist. In Tegmark's framework, the end of time might not be universal. Some mathematical structures could permit eternal dynamism, while others inevitably freeze. Our universe might be one thread in a grand tapestry of equations, some still churning with activity, others locked in static completion. This leads to a chilling question: are we in a universe whose equation is winding down? The accelerating expansion of space, the relentless rise of entropy, these could be clues that our cosmic Rubik's Cube is nearing its final twist. The mathematical universe hypothesis does more than predict an ending. It redefines what an ending means. No fiery collapse, no fading embers, just the silent satisfaction of a theorem resolved. Time wouldn't stop because something interrupts it, but because it's no longer needed, like a clock that ticks until the work is done, then rests. And in that stillness, perhaps, lies the ultimate truth. That reality was never about stuff or forces, but about the beauty of a perfect proof, eternally complete. We think of time as a river, something that flows from past to future, carrying us relentlessly forward. But what if that's just an illusion? What if time isn't moving at all? This is the mind-bending essence of the never-ending now, a theory that strips away our linear perception to reveal a universe frozen in a single, eternal present. No beginnings, no endings, just an infinite tapestry of moments, all equally real and unchanging. This idea isn't just philosophical speculation. It's rooted in Einstein's theory of relativity, where time is woven into space-time as a dimension no different from length or width. Picture a block of marble. To a sculptor, the statue already exists within it. They're just revealing it piece by piece. In the same way, the block universe theory suggests past, present, and future are all equally real, laid out like landmarks on a map. Your birth, your first heartbreak, your last breath, they're not ahead or behind you. They're just there, fixed in the cosmic fabric. Human consciousness, though, rebels against this view. We experience life as a sequence, a parade of nows that feel fleeting and unique. But neuroscience hints that even this might be a trick of the brain. Studies show our perception of the present is actually a constructed narrative, a stitching together of sensory inputs with a slight delay. When you hear a knock at the door, your brain has already predicted the sound before the signal arrives. Your now is a best guess reconstruction, not a live broadcast. The implications are staggering. If time is static, then free will crumbles. Every choice was predetermined the moment the universe began. Mortality, too, loses its sting. Death isn't an endpoint, it's just another coordinate in the block, no more final than your first step or your first kiss. Some physicists, like Julian Barber, take this further, arguing that change itself is an illusion. That reality is a collection of frozen nows, like frames in a film strip, with motion arising from our limited perspective. Yet here's the paradox: even if time is an eternal present, we're wired to resist that truth. Our languages are built on tenses, our cultures on progress, our emotions on anticipation and memory. The never-ending now doesn't just challenge physics, it confronts the very core of human experience. How do you find meaning in a universe where everything has already happened? How do you cherish a moment that was never truly fleeting? Perhaps the answer lies in the tension itself. The universe may be static, but we're dynamic observers carving stories into the void. Time's end isn't just meaningless, it's impossible, because in a never-ending now, there's nothing to end, only an infinite canvas waiting to be seen. From the violent collapse of the Big Crunch to the silent fade of heat death, from the digital shutdown of cosmic simulations to the eternal reset of the Big Bounce, we've journeyed through 30 wildly different visions of how time might meet its end. Some are grounded in meticulous physics, equations scribbled on chalkboards by the world's sharpest minds. Others feel ripped from ancient myths or dystopian nightmares, where gods, machines, or even our own consciousness dictate reality's final moments. Yet what unites them all isn't just their subject, it's humanity's burning need to stare into the void and demand answers. Think about it, every culture, every era has wrestled with this question. The Mayans carved its countdown into stone. Einstein wrote its equations on napkins. Modern physicists probe for clues in the spin of particles or the glow of dying stars. Whether through science, philosophy, or sheer imagination, we've always been obsessed with time's limits, not just because we fear the end, but because understanding it might reveal what we truly are. Are we fleeting flashes in a cosmic storm, or threads in a tapestry so vast even endings are just stitches in a grander design? What's astonishing isn't just the variety of theories, it's how each one reflects a different facet of our psyche. The Big Rip mirrors our dread of being torn apart. The Omega Point channels our hope for redemption. Even something as bleak as Proton Decay carries a weirdly beautiful truth that everything, even atoms, has an expiration date. These aren't just predictions, they're Rorschach tests for the soul, revealing what we value, what we fear, and what we're willing to believe. So now it's your turn. Which of these endings resonates with you? The poetic cycle of the Big Bounce, the chilling finality of Vacuum Decay, or something even stranger like Boltzmann Brains or quantum immortality? Drop your favorites in the comments. Let's geek out over doomsdays together. And if you're hungry for more mind-bending mysteries, hit that subscribe button. The universe is full of puzzles, and we're just getting started. After all, time may be running out, but the curiosity, that's eternal.